Bordine-Taber simple adhesion theory. In the Bordine-Taber simple adhesion theory, they told that when the two surfaces are loaded, the intimate contacts occurs at the peaks of the asperities. Okay? So they occurs at the peaks of the asperities. See here, this one. Only at the peaks of the asperities there will be a contact in the beginning, and when the load increases, means when these two surfaces come closer to each other, there what happens? This contact grows. So initially the area of contact was very small. When there will be more pressure on this upper surface, when more load on the upper surface, this contact will deform and it will become flat, so that more area of contact will be there. And when there is more area of contact, friction goes on increasing. Okay, that was the Bordine-Taber simple adhesion theory in the last class what we have seen. But there were some limitations of that Bordine-Taber adhesion theory. What were these? The first inadequacy was that the friction coefficient does not depend only on the property of the softer material, but whereas in Bordine-Taber theory they have taken that the softer material is the one which will deform. So shear strength was of softer material. So this S is the shear strength of softer material. Whereas actually speaking, it does not depend only on the shear strength of softer material, but it depends on other properties also. That is material properties of the harder material also. Okay. And under normal atmospheric condition, the actual value of coefficient of friction was 0.5, but whereas from Bordine-Taber theory, we calculated it as only 0.2. This is also one more contradiction. And third one was friction was very much higher actually in ultra vacuum conditions and under contaminated free sliding conditions, which was not explained by Bordine-Taber simple adhesion theory. So due to this, what happened? This Bordine-Taber adhesion theory was modified, and they called it as modified adhesion theory. It is called as modified adhesion theory or junction growth theory. Okay. In the modified adhesion theory, the drawbacks of simple adhesion theory led to the development of modified adhesion theory. Professor Bordine-Taber re-examined their own theory. Their earlier theory, whatever they have told, they re-examined it, and they themselves have modified their own theory. And they called it as modified adhesion theory. What they did is they modified considering the combined effect of normal and shear stresses. In the previous theory, there was only shear stress was taken into effect, into consideration, but whereas here they came to know that it is not only the shear stress, but normal stress will also play the major role in generating the friction. Okay, so due to that, what happened? They have taken both normal strength and also shear strength. S is the shear strength, whereas P is the normal strength. This is unlike the earlier case where the effect of normal and tangential loads were considered separately. So there the effect of normal and shear stresses were considered separately in the previous theory, but whereas here they taken the combined effect of these two loads, that is normal load and also shear load, and they told that while calculating friction we have to take the combined effect of both normal load and shear load. Okay. It was considered that the normal load determined the real area of contact and the shear over this area. Tangential force was needed. But the very high friction coefficient observed in the case of clean metals point to the fact that the true contact area must be much greater than the predicted by the normal load alone. So they came to know that by experimentally, actual contact area is very much larger than what is predicted by the area of contact due to only normal load. That is why they have taken normal load also and shear load also. Okay. Hence, let us consider an element subjected to uniaxial compression by a normal stress P naught. Okay. Let us consider that there is one. Let me. Okay, let us consider that two surfaces are there, one above the other. Okay, so here it is applied by a normal load of P naught. P naught is the load acting on the two surfaces which are coming in contact, and due to this P naught they are under compression. So we can assume it to be on the point of yielding. If a tangential stress is now applied to it, okay, suppose if you apply a tangential stress now, that is yes, okay, let us apply tangential stress, that is the stress parallel or load parallel to this area, that is sliding load. Yes, like this. There what happens, it will generate certain stress called as shear stress or shear load. Okay. If a tangential stress is now applied, it experiences an additional shear stress. Yes. For the material to remain at the point of yielding, the normal stress on the element must reduce to some value P1. So at the point of yielding, what happens, when the yielding starts, the material will start deforming, so that load goes on decreasing, no? So in the stress strain diagram or load deflection diagram in material science lab or material testing lab, what we did, when we start loading using universal testing machine, until necking the load is proportional to deflection, but once the necking starts or once the material starts yielding, what happens, load decreases whereas deflection increases, no? So that is why this curve dips. So let us consider that due to this yielding, the load has decreased to say P1. Initial node is P naught. It has decreased to P1 after yielding. And S is the shear stress or tangential force applied on this surface. If the normal load remains constant, means if the normal load does not change, then what happens? The area of contact must grow. That is, initially the area of contact is very, very small, and as the area of contact here. See here, let us take these are the two areas, two surfaces which are coming in contact with each other. You go on joining these fingers together slowly. In the beginning, what happens? The area of contact is very, very small. You just see the contact between the two fingers. The area of contact is very, very small. No? When you press the fingers, means when the load goes on increasing, what happens? This finger will become flat and this finger will also become flat. No? And the area of contact here. In the beginning, it was very small point contact, but when you press it together, the area of contact increases, no? So this is called as junction growth or the increase in contact area. Okay? So the same thing happens in the two materials also. In the beginning, when the two materials joins together, only the asperities are contacting each other. But when the load goes on increasing or when the time goes on increasing, there what happens? You can see here that. See here, in the beginning there was very small contact, but whereas as the area goes on increase, as the load remains constant and the material start yielding, means material start deforming, there what happens? The area of contact goes on increasing, means what? The area of contact grows. This is called as junction growth. It is a junction of two materials and which is growing. In the beginning it was this much, now it is this much. So this is called as junction growth, which was stated in the modified adhesion theory. But in the modified adhesion theory, they have taken both shear stress and normal stress into account. But whereas in the beginning, in the adhesion theory, there was only shear stress was considered. See here. Then the area of contact must grow. This phenomena is thus known as junction growth. For a Tresca criteria, the relationship between P1S and P0 is given by. This is the criteria which we have used in machine design 1. Von Mises criteria, Tresca criteria, no, those failure theories. Von Mises theory, Tresca theory. So, according to Tresca theory, it is P1 square plus 4S square is equal to P0 square. But according to Von Mises theory, the yield criteria is given by P1 square plus 3S square is equal to P0 square. These two equations were taken from design 1, machine design 1. Okay. Both the relationships lead to the same qualitative conclusions, though they differ in the coefficient of S square. In both the cases, coefficient of S square is different. Here it is 4 and here it is 3. But both will qualitatively lead to the same conclusion, that is growth in the junction. Now, if we use P1 is equal to W by A, that is pressure P1 is equal to load by area, and stress is equal to shear stress is equal to shear force by area. If F is applied in this direction and area of contact is say A, then S is equal to F by A. Whereas P1 is equal to W by A, where W is the normal load applied on the body and A is the area of contact. So F being the tangential load. Then equation reduces to, you substitute. So P1 square will become W square by A square and S will become F by A. Yep. Okay. Hence, once you substitute this W by A, P1 is equal to W by A and S is equal to F by A, you will get this expression in this above equation. That is in equation 5.6, if you substitute these two, you will get this equation. Okay, W square plus 4F square is equal to A square P0 square. A square we have taken common and sent it on this side. Okay. Then the maximum so in any typical dead weight sliding experiment, W is constant. Okay, W is constant always. Okay, load applied on the body, while P0 is a property of the material. So P0 is what? It is a property of the material, that is yield stress of the material, that is stress in the material, normal stress in the material. The real area of contact A will thus increase with increasing the tangential force. As the tangential force goes on increasing, the area of contact also goes on increasing. Hence the ratio F by W, the instantaneous value of coefficient of friction, will also increases. So F is equal to what? Mu into W, that you have seen. F mu is equal to F by W. So F by W also goes on increasing. The instantaneous coefficient of friction F by W goes on increasing. Okay. Theoretically, the growth process could continue until the entire area of specimen is in contact. Theoretically speaking, what happens when the two areas are coming in contact? See here you can see that when this load goes on increasing, what happens? Initially beginning only small contact will be there, but as the load goes on increasing, the contact also grows. And up to what extent these contact will grow? Up to when all these voids are removed, means when both the surfaces will contact firmly. with entire surface area of one surface. Okay? Then that is the theoretical growth process. But the actually what happens due to the effect of weak interfaces, in most practical cases, the ductility of the material and the presence of weak interfacial films limit it. So due to that, what happens? Small amount of voids will always be present in between the surfaces. So the surface will not completely entirely contact with each other practically, but whereas theoretically speaking, it may contact. Okay? Thus, the effect of weak interface can be modeled, assuming that it will fail at some shear stress value SI. Okay? Okay. Let us take that SI is the stress at which this junction will fail. Means the junction will break and the material start sliding. The surfaces start sliding on each other. Let SI be the shear stress. Okay. Then the maximum tangential force is given by F max is equal to A into SI, where SI is the shear stress at which the junction breaks. SI is the shear stress at which the junction breaks. If the shear yield stress of the bulk material is S0, if S0 is the yield stress of the bulk material in shear, then from Tesca yield criteria, P0 is equal to 2 into S0. Hence, the coefficient of friction can then be derived as mu is equal to F max by W. That is 1 by 2 under root S0 by SI bracket square minus 1. So this is the equation of mu based on modified adhesion theory. If the interface has the same shear strength as that of the bulk material, then mu becomes infinite. Means what? When S0 and SI are equal, what happens? It's when yield stress of the when material is equal to the strength of the junction, then what happens? This will become 1. So this 1 minus 1 will become 0. So 1 by 0 is infinity. Means what? Friction becomes infinite at that time, but which is not possible practically. Okay? When the interface is weak, mu is finite. Means what? If the strength of the junction is lesser than that of the yield stress of the material, then what happens? Mu will be having a finite value, and it mu goes on decreasing as the ratio SI by SO falls. As SI by SO goes on decreasing, mu also goes on decreasing. The dependent of mu on this shear strength ratio SI by SO is shown in figure 5.4 here. This is the ratio SI by SO, and this is coefficient of friction. So as SI by SO goes on increasing, coefficient of friction mu also goes on increasing like this. Up to a certain extent, it is flat with a certain slope, but after here about 0.9, suddenly the slope increases. There is a steep rise in coefficient of friction. So what we have to do? We have to operate all the machines within this range only. This range of SI by SO, that is up to 0.6 SI by SO ratio. So that coefficient of friction will also be lesser. Okay. The figure shows that an interferential strength 1/10 of the bulk value mu is equal to 0.05. For interface with half the bulk strength, that is at 0.5, mu value is something around 0.3 here. At 0.5 value of SI by SO, mu value is about 0.3. But whereas when this goes on decreasing, mu value also goes on decreasing. Thus, the weak interfacial films lead to very limited junction growth and reduce the value of mu. If a film of material of low shear strength can be incorporated between the two surfaces, then the coefficient of friction can be lowered. This is about modified adhesion theory. So the next one is the last theory, that is deformation theory or flowing theory. This is dependent completely on different principle. In the adhesion, simple adhesion theory and modified adhesion theory, they were of the interference that the friction coefficient of friction between the two material is due to the adhesion between the two materials at the point of asperities. At the asperities, whatever the adhesion occurs, the junction will grow. Due to that, the friction will be existing. Like that, the first two theories have devised. But whereas in the third theory, that is deformation theory or flowing theory, this is completely different. In the flowing theory, what happens? When the two materials slide on each other, the softer material will deform or will wear, and the small wear particles will be existing between the two surfaces, and they get trapped between the two surfaces. And you can see that the wear surfaces may be of any shape. They may be conical in shape. The wear debris, what we call it as, the wear particles are called as wear debris, DEBRIS, wear debris. Okay. The wear debris may be of different shapes. It may be conical in shape, or the wear debris may be spherical in shape, or it may be upright cylindrical in shape. Upright cylindrical means vertical cylinder, or it may be transverse cylinder, means in horizontal cylindrical phase shape. Okay. So here this wear debris, wear debris. So for example, suppose you want to sharpen any tool on that grinder machine in our workshop. What you do? You go on holding that tool on the grinding wheel, no? And when you hold the tool on the grinding wheel, small particles will be falling down. No, those are the wear particles of the tool. Those wear particles are called as wear debris, and those wear debris will be of different shapes. They may be either conical or spherical or upright cylindrical or transverse cylindrical. And when those wear debris gets trapped between the two surfaces, and when you slide one surface on the other surface, due to those wear debris, which are very hard particles, they will put scratches on the surface. Initially, the surface was very smooth. Due to that wear debris trapping between the two surfaces, they will put some scratches on the surface. That is, the scratches, those scratches will remove the material from the surface. That is called as flowing. Flowing, flowing means the flowing you do know in your field. That is negla hodidu. Holdag negla hoditarla. So there what happens? So when they are flowing, what happens? They will plow the land, and when they plow the land, at that time that patches are produced on the land, those lines, and the material, that material is removed from the land, and that material, those wear debris or what those material or the soil will come to the side. So that is called as flowing. So here also the same thing will happen when the wear debris gets trapped between the two surfaces. Okay, there will be flowing. Therefore, the normal load W is supported by the horizontal. So here what happens in cases where the adhesion is very small, this deformation theory will hold good only when the adhesion is very small. Okay, there is no any adhesion between the two surfaces. Then what happens? The two surfaces will start sliding on each other, and the flowing becomes a dominant component of friction in that case. That is, the third theory will hold good in that case. If one of the surface is sliding contact is harder than the other, then what happens? the asperities of the harder surface may penetrate and flow into the softer surface. The asperities or projections on the harder surface, what they will do? They will penetrate into the softer surface and they will flow like a flowing tool. Negled hang chup andirthe ಆ type asperities ಏನಾಗ್ತಾವು, they will start flowing. Those asperities of the hard surface, they will start flowing the softer surface. Flowing may also occur as a result of impacted or entrapped wear particles. If wear particles get trapped, there also the flowing will happen. If the asperities of the harder particle will put scratches on the harder surface will put scratches on the softer surface, there also the flowing may happen. The interaction of two rough surfaces may result in mechanical interlocking, okay, on a micro or macro scale. Okay, when there is a flowing, what happens? There will be mechanical interlocking between the two surfaces. That is, when this asperity of the hard surface penetrate into the soft surface, they cannot slide easily. And due to, as they cannot slide easily, that is, the friction goes on increasing. So that is the main cause of friction in the third theory. That is, when the adhesion is very, very small, only at that case, this third theory will be existing. That is, the friction will be due to flowing. Okay. This flowing not only increases friction, but also creates wear particles, which in turn increases subsequent friction and wear. Those wear particles will again increase the friction and wear because of putting scratches on the surfaces. Flowing component of friction may be calculated using model rigid asperities or entrapped wear particles. So in order to calculate the how much flowing has happened, so what we have to do, first we have to consider what type of wear debris are there, what are the shapes of the wear debris. That is, the wear debris may be, or the asperities may be of conical shape, spherical shape, or upright cylindrical shape, or transverse cylindrical shape. So during sliding, only the frontal surface of the asperity comes into contact with the softer surface. Therefore, the normal load W is supported by the horizontal projection of the asperities contact area. Considering the yield pressure of the solid as P naught and the yielding of the body to be isotropic, let us consider that the material is isotropic and P naught is the yield strength of the material, then load W is equal to P naught into area AH, and that is horizontal area, and F is equal to P naught into AV. This is due to sliding. This is the shear load and this is the normal load. So normal load will depend on horizontal area, whereas shear load will depend on vertical area of the asperity. Okay. So W is equal to P naught into H and F is equal to P naught into AV. Okay. Then thus the coefficient of friction due to flowing is given by mu P is equal to F by W, that is AH by AV. Okay. This P naught get cancels, so it will remains AH by AV. Okay. Then see here, these are the different shapes of the asperities. The asperity may be conical in shape. This is when the asperity is spherical in shape. This is when the asperity is transverse cylindrical in shape. This is when the asperity is vertical cylindrical in shape. Okay. And this is the force F, that is in the horizontal direction, that is the shear force, and this is the load W, which is the normal load. Okay. Then you can see that for a conical asperity, the area, vertical area is given by 1 by 2 into 2 into R into D, where R is the radius of the cone and D is the depth of the cone. That is, this is D, how much cone is penetrating in the soft material, that is D is the depth, and R is the radius at this point. That is, this is diameter 2R. So this is radius half r. Okay. So 2r is the radius and d is the depth of penetration. Okay. When it is like that, then at that time the area is given by vertical area is half 2 into r into d, and horizontal area is ah is equal to half pi r square. Now substituting these in the above equation, so mu p will become 2 by pi cot theta, that is cos theta, 1 by tan theta. What is 1 by tan theta? Cot theta. Okay, that is 2 pi cot theta. Then suppose the asperity is of spherical in shape, then what happens? For a spherical asperity of radius capital R, if capital R is the radius of this spherical asperity, spherical means it's like a ball, completely sphere. Okay. In that case, horizontal area is given by half pi r square and vertical area is given by half r square 2 theta minus sin theta. Okay. Then, but we know that the sin theta series which we have used in the first year in C programming, you have used this series, no, sine series. It is this one, sin theta is equal to 2 theta minus 2 theta cube by 3 factor. Like this, it continues. Then for small value of theta, AB is equal to half r square 2 theta minus sin 2 theta plus 2 theta minus 2 theta plus 8 by 3 factor. Is this one. 2 cube is 8 divided by 3 factor, and this minus into minus is plus. So it will become 2 by 3 r square theta cube. And again, we know that sin theta is equal to small r by capital R, which is almost equal to theta. Therefore, for small theta, AB is equal to, substitute theta is equal to r by r here. So it will become 2 by 3 small r cube divided by capital R. And mu p is equal to, you know that, AV by AH. So substitute AV and AH. You will get coefficient of friction mu p is equal to 4 by 3 pi small r by capital R. This is for spherical asperity. For comparatively large width of the groove with respect to the radius of sphere, mu p is given by, if the width of the groove is larger than the radius of the sphere, then mu p is from this equation. Then for the case of a transverse cylinder shown in figure, transverse cylinder means what? Horizontal cylinder. Here horizontal area is L under root of r square minus r minus d bracket square. It is L into 2r minus d. That is, expand this bracket and cancel r square, it will become 2r minus d into d. And AV is L into d. Thus mu p is equal to AV by h, that is 1 by root of 2 r by d minus 1. Then for the case of an upright cylinder, means what? Vertical cylinder, then we'll get AH is equal to this one and AV is equal to this one. So coefficient of friction mu is equal to AV by AH. Okay. So this is the flowing component of friction, and flowing component of friction can be reduced by reducing the surface roughness, selecting materials of more, less or same hardness. Okay. What you can do, this flowing component of friction can be reduced by either reducing the surface roughness, means making the surfaces more smoother, or and by selecting materials of two surfaces whose hardness will be same, so that both will become harder surface, so that there is no flowing of the softer surface. And by removing wear particles from the interface, this is very important. When the wear debris are formed between the two surfaces, we have to flush them out. We have to remove them out from between the two surfaces. That wear debris should not get trapped between the two surfaces. That is why in IC engine, when the piston is reciprocating inside the cylinder, at that time what happens? When the lubricating oil is continuously flowing with the help of a pump, that lubricating oil will flushes the wear particles. That is one function of the lubricant. It will flushes the wear debris between the two surfaces so that the surfaces are not damaged further.